Okay, can you see the slide?
Yes, sir.
Okay, fine. Fine. So we will now study details of the TCP protocol, which is widely used on the internet all the time. Okay. Uh, in the previous topic, we have studied general overview of the transport layer protocol. This is the topic on which you will have your second class test on coming Saturday. But today, from today onwards, we will now start covering the technical details of the TCP protocol, which is the Common Transport Layer Protocol. Of course, you will find that most of the concepts that will be used has already been covered. Okay, however, now there will be some details which are particularly used in TCP, which will now be basically described to you. Some peculiarities of TCP, some extraordinary features of TCP. Okay, these type of things will now be covered to you. Some history. TCP was originally designed to provide a reliable end-to-end byte stream over an unreliable internet network. In fact, any transport layer protocol does it. Now, this inter-network terminology was first used in 1974. Okay, I'll come to that. But what is an inter-network? In an inter-network is a different collection of topologies, bandwidths, delays, packet sizes, different parameters. Okay. So your entire network need not be homogeneous. Just to give you an example, you might have right now, say for example, I am now teaching the class from through a wireless internet connection. Okay, so I'm teaching it the class from my laptop, which is using a wireless internet connection. But then there is a wired connection. There is a modem, wireless modem, which is transforming it into electrical signals, which is getting carried away by my telephone connection, which is there at my home. Okay, inside campus. So in this way, then probably it goes to even more broadband trunk connection, the BSNL trunk connection that is there to IIT, which is optical fiber connection. Okay, then it goes to from here to Kolkata, etc., etc. So over different topologies, over different widely differing bandwidths at the network layer, the transport layer protocol will work and it will give seamless service. Okay. So TCP should dynamically adapt to the properties of the internet network and it will be robust to face many kinds of failures. Some of these failures we have already discussed. Okay. For example, there are issues regarding setting up of connection, stripping down of connections, between loss of data packets and repeated delays of data packets, delayed duplicates, crash of a server, and again it's coming up. All these different things will be handled properly and it will give a faithful service. It was first proposed in 1974 by Vincent Cerf, professor of Stanford University, and Robert Kahn, a DARPA scientist, as a monolithic combination of what is now TCP and IP. Okay, so it was called TCP, and the word internetworking was used for the first time in this document in 1974, some publication, and it was shortened to internet. So basically not the internetworking word probably, but the internetwork as a shortened version of internetworking was used for the first time in 1974. Interestingly, it was a combination of both the transport layer protocol as well as the network layer protocol. However, they were separated in 1981. Okay, to be two different protocols. For their contributions to foundational contributions to computer networking. Cerf and Kahn received the Turing Award in 2004. Turing Award, as you know, is kind of the Nobel Prize of computer science. In September 1981, the basic description standard was published. It's RFC 793. Then there have been several enhancements and modifications, etc. Some of which we will study. Interestingly, one very important feature which made TCP/IP kind of a global standard in networking was the operating system kernel's direct support for this. And that support started happening with the BSD version of Unix in 1983. BSD is Berkeley Standard Distribution. It's a version of Unix developed at Berkeley, partially with support maybe from AT&T. Actually, AT&T was the original developer of Unix. But then that company gave it for free evaluation to many universities around USA. Berkeley was one of them, but I think then there was some spat between the company and the universities. So Berkeley decided to develop its own version of Unix, and that's how BSD was developed. BSD and its several variants are still available. Okay. Anyway, so once the operating system directly started, kernels directly started supporting TCP/IP through its network stack, that became a huge advantage for developers. Before this, the support of TCP/IP in Unix was very minimal, and it was very difficult actually for application developers to write programs. Okay. Now, how does TCP work? TCP uses something called sockets to define an end-to-end connection. Socket is basically a data structure with several parameters: the source IP, source port, source initial number, destination IP, destination port, destination initial sequence number. So all these different parameters define sockets. These data structures are maintained by the operating system. Sorry, I got disconnected. Can you hear me now?
Yes, sir.
Up to what point did you did you get to hear the socket part?
Yes, sir. The socket data structure
Yeah, so
element.
the socket is kind of the basic mechanism through which the TCP works. These are data structures maintained by the operating system to kind of differentiate every connection. There are several parameters which fundamentally describe this every instance of this data structure. The important parameters are source IP address, source port, source initial sequence number, destination IP address, destination port, and destination initial sequence numbers. Okay, so the concept of a port and initial sequence numbers have already been described. Source IP you have an basic idea because you have already, those of you particularly in the lab, have already started using that in your assignments. But the details about IP addresses and the formats of IP addresses, the dotted notation, decimal dotted notation, everything will be covered when we study the network layer in detail. Okay. How we the socket implementation and the TCP service model, the connectivity works? Well, every operating system when it boots up, it starts a super server daemon process, okay, called internet daemon or inetd in short. It is usually under /user/sbin directory, and this inetd process, it runs all the time at different well-known ports which are used for different services. Okay, for example, HTTP, FTP, etc. And it waits for the first incoming connection at that port of that type. So it is waiting for the first HTTP connection, etc., etc. Now, when suppose a first connection of that type comes, inetd forks a new process, okay, and starts the corresponding daemon. For example, the daemon which supports the HTTP protocol, okay, is the HTTP daemon at port 80. The daemon which will support the FTP protocol is FTPD at port 21, etc. I shouldn't call protocol. I mean, these are protocol and services both. So inetd is kind of the super process which spawns its child daemon processes. So this is the father of other daemons. Okay, so this is a like the super daemon process. This is an important concept to tell you that Unix doesn't unnecessarily, as soon as it boots, starts to spawn all the daemon processes at the different ports. For example, FTP is something which is not that well. It can be used, but it is not that commonly used. Also, maybe. Okay, for example, the straightforward version of FTP, the not SFTP, the unencrypted version of FTP is blocked on IIT computers inside the campus. On the departmental computers, FTP is blocked because it is not secure. Okay, so what is the point of starting the FTP daemon on a Linux system? If you know that no, it is anyway, so I mean, this is blocked. The firewall will block this, and as per the prevailing network practice in this organization, FTP will never be used. So there is no point doing it. Okay, starting the daemon. So it only starts the daemon when the first connection request of that type comes at that port. Okay, then it starts the corresponding service daemon. All TCP connections are full duplex and point-to-point logical connections. Again, this is a logical connection. Please remember, TCP will give you an idea that as if it is a physical connection, it remembers everything, how many bytes have gone from this side to that side and vice versa. Okay, but it is not a physical connection. It is a logical connection. Okay, this is a very, very important concept. There is, by physical connection, it means that resources are for the entire session. Resources are blocked between the two parties. They are reserved. This is not like that. We have described this earlier also, the difference between a physical connection and a logical connection. A telephone, landline telephone connection is a physical connection. Okay, because for the entire duration, the bandwidth or a portion of the bandwidth between the two communicating parties is reserved for the call. Whether you talk or not, that doesn't matter. You are keeping silent. Both the parties are keeping silent, but still the bandwidth is reserved for the entire duration of the call for these two parties. So this is different from TCP. TCP will on segments will only generate network datagrams when the need comes. Okay, and there is no reservation of anything for anybody. And TCP does not support multicasting or broadcasting. Okay, you cannot send multicasting and broadcasting are concepts where you try to send messages, one message to multiple parties. We will study this concept, multicasting and broadcasting, in detail when you study the network layer. Okay. Network IP datagrams can be broadcasted. Later on, we'll see through in certain situations it is necessary. However, TCP is not like that. TCP messages cannot be sent to multiple parties. To compare, this is different from, this is similar to landline, old-fashioned landline telephone connection, and it is different from, say, a WhatsApp group voice call where there are multiple parties. Okay, so you can speak and the message gets delivered to all the parties connected in that call at the same time. TCP does not work like that. It does not have the ability to work like that. TCP connection is a byte stream, not a message stream. This is a very, very important concept. Okay, this is I would say probably the most important concept of the this entire topic. TCP does not understand what is the meaning of a human readable message. Okay, it does not care about whether the message should be broken up into small chunks or not. If it feels it has to be broken up, it will break it up. So it doesn't care of what is a sentence, what is a paragraph, that, okay, if I do not send one sentence in one segment, I will need another segment for the same sentence to wait, and only then I will have the full sentence. Okay, if this is the situation, and it is unfortunately, it is not unfortunately, this is how TCP works. So it is the responsibility of the application layer program which is using the transport layer service to properly assemble the segments to build up a meaningful message to be presented to the human user if needed. Okay. Message boundaries are not preserved end to end. Okay. For example, say the sending process does you can control how much data you want to write through different calls. Say you have an system call called write. You do a system call you do a system call execution of write to the TCP socket, and you write 512 bytes. Now the question is, your application is doing a write of 512 bytes to the TCP socket. Is it guaranteed that these 412 byte chunks, you do 4 512 byte write operations successively? Are they guaranteed that this will exactly be communicated as 512 size data segments? No. It can be anything. It can be 4 512 byte chunks, 4 2 1024 byte chunks, 1 2048 byte chunks, or in any other way. It doesn't care. Okay, it doesn't care. Whatever it can do, it does. Okay. There is no way for the receiver transport layer entity, the receiver TCP daemon, to detect the units in which the data was originally written by the sending process. Okay, this situation is slightly similar to the physical layer address and logical address thing that that programmers face. We use logical addresses, okay, or virtual addresses to write in our programs. Okay, what is the ultimate physical address of the data that is getting stored finally is not clear to us, because there is the operating system and associated hardware sitting in between, which performs a logical address to physical address translation, which is not transparent to the application programmer. Okay. Similarly, in a TCP case, the application programmer can control the amount of data it is writing, but it cannot control the segment sizes. Very soon we will see the organization or the structure of a TCP segment. There you will find that there are two distinct components, a metadata component, which is a header, and then the actual data. How much data will be there is variable. There is an upper limit on how much maximum data can be there, but there is an it is not guaranteed even under the upper limit. Even if you stay under the upper limit, it is not guaranteed how much data will be there in the segments, each segment. This is the TCP header. Please pay attention. Okay, try to understand a little bit. Intentionally, this first of all, understand this. Please understand that the TCP segment, this is actually the TCP entire TCP segment. First, you concentrate on the header. Okay. Intentionally, to make it easy to explain, this two-dimensional structure has been given. If you look on the top, it's a 32-bit kind of width, where most of the fields are word aligned. If you consider 32-bit to be one word, some of the fields are half word. Some of the fields are even smaller, etc., etc. 4 bits, etc. First, let's try to understand the different fields of the header. The header is at least 20 bytes. Okay, why I say at least, very soon you will understand. First of all, please understand that each row of this is 1 byte, is 4 bytes. Okay. So if the header is at least 20 bytes, the header has at least 5 rows. The actual TCP segment is not, there is no concept of this two-dimensional thing. Okay, every field is one after the other in proper width. Just to explain it in easily, there is this two-dimensional structure given to you. Okay. Now, in this two-dimensional structure, every row is 4 bytes. In that case, if the header is at least 20 bytes, it should have at least 5 different rows. So let us see this row structure. The first 16 bits is the source port, then 16 bits is the destination port, then 32 bits is the sequence number, then 32 bits is the piggyback acknowledgement number. Remember, we discussed that the acknowledgement number is always piggybacked on the segments. Usually they try to avoid sending only acknowledgements. However, there are situations, as we have seen in sliding window protocols, that there might be situations where you send back only the acknowledgements, or even in maybe sliding window, or in also in stop and wait. Okay. This TCP then okay. This TCP header length, interestingly, is only 4 bits. And please understand that this the interpretation of this header length in 4 bits is not in bytes. The TCP header length describes the number of 4-byte words that are there in the header, including itself, because it is only the fourth row. Okay, there are one additional row extra, and then there are options, but this TCP header length basically says that these are the number of 32-bit words that are there at least in the header. Then certain fields are kept in empty. Okay, how many bits are kept empty? Well, TCP is 4, and here there are certain 1-bit flags, which are 0 means unset and 1 means set. Very soon we will study some of these flags. Okay, 1, 2, 3, 4, 5, 6, 7, 8. 8 flags are, so 8 and 12. 8 and 4 is 12. Remaining 4, this shaded portion, these are unused fields. Some of them have started to be proposed to be used. Okay, but they are not yet global standards. So some implementations might support them and some might not support them. Okay, so these are kind of considered to be unused fields. Then there is a window size. The TCP connection, as we have studied earlier in the transport layer mechanisms, the receiver advertises the window size that it can support, and it forces the sender to use that window size. Okay, so that the force unnecessarily the sender does not push too much data into the connection and overwhelm everything. The checksum is a 16-bit checksum to calculate the entire validity of the contents. The calculation of this checksum is somewhat complicated. We will study it later on. How is this done? We will study it later on. Give me some time. In the later class, probably next week, we will study. Similarly, there is an urgent pointer, which also is slightly complicated concept. We will study it later. Now, interestingly, this can be considered to be the end of the header, but interestingly, there are certain options. These options are 0 or more 32-bit words. So if these options are there, then they will entirely occupy 32-bit 4-byte chunks. Okay, but there need not be any options. Several options in TCP are supported. Okay. Again, we'll not probably go into the details of all of this. You can find these details if you study some TCP/IP handbook or those type of books. But several options are supported. Unfortunately, these options have been misused by certain parties to attacks also, because the options are not always checked. Okay, what is there inside these options are not always checked by all implementations, and then many bad things can happen. Again, that's probably a network security concept, so I'll not go into it. Then after these options finish, and remember that if the options are present, they will occupy 4-byte chunks, entire 32 bits. So maybe one or more further rows. After those finish, then the data starts. So the TCP header length that will be present would basically mean the total number of rows before the data starts, because it works in terms of number of 32-bit words. Do you get it? So the TCP header length will also include the option. If there are options, that will also be included in the TCP header length. That's why the TCP header length is important. It needs to tell how many option fields are there. Otherwise, this packet cannot be parsed. Where the options are ending and where the data is beginning, it will be very difficult to understand, because TCP does not make any sense of the data. It just treats everything as streams of bytes. So to it, if there was no way to differentiate between where the urgent pointer ends and from where the data begins, then it might start to treat everything starting from the end of the urgent pointer to be data. But that's not the case. There might be one or more rows which are actually options. Okay. So the TCP header length essentially is the total number of 32-bit words in the header. And if you look at this two-dimensional representation, it is the total number of rows after which the data starts. If you consider, say, the rows start from row number 0, then row number 1, etc. So if, say, the TCP header length is like, say, 7, then 1, 2, 3, 4, 5, 6, 7. So there are two options. So 7 rows will pass from row number 0 to row number 6, and the 7th row will be the starting of the data. Interestingly, the amount of data that has to be present is also optional. Means it need not have any data. Okay, it is not essential that it must contain any data. So there can be a blank, there can be a segment without any data also. Okay, so why is, students, can you give an example of a situation where this is useful? Means, do all TCP segments actually need to transfer data? Or sometimes you also send segments where no data needs to be sent.
Connection initiation request and acknowledgement, only acknowledgement.
Yes, connection initiation, acknowledgement, then connection finish, then in between anywhere other than connection. Your answer is correct. During connection initiation and connection termination, these might be situations where you do not need to end any data, send any data. Any other situation that you can think of? There is some sound actually.
Hello? Is it audible?
Yeah, there is a lot of echo. We cannot hear you. Yeah. You can write in the chat box also. Maybe I can read it out for the class. See, in between, sometimes for repeated segments, you send back only acknowledgements. That time, yeah, to maintain the connection, yes, that is true. Sometimes, as we will as we will see, that sometimes to maintain the connection, certain packets are sent. Where do you send it? We will find. But it is also sent when you basically we have seen that situations where you send back only an acknowledgement mentioning the packet that is expected, segment number that is expected next. Okay, in those situations, this type of thing is very useful. Okay, to maintain the connection where it is used, we will come to it some example later on, but the answer is correct. Now let's continue. So okay, so one important concept is every byte on a TCP connection has its own 32-bit sequence number. Okay, which is a byte stream because it is a byte stream oriented connection. Every byte. So if 1000 bytes are sent in one segment, the next segment will have bytes starting from number n plus 1000. Okay. So in this way it works. So you might say it's a 32-bit sequence numbers for bytes is too small. It is not too many bytes. 32-bit is how much? It is like maybe 65,000 something. It is not a big number. Yes, it's probably not. This 32-bit is no 32-bit is say 2 power 30 is well, no, it's not 65,000. Sorry, it's reasonably large, but still it's not that large because nowadays so much data is transferred, so it's not a very large number. But we have discussed these things that it will wrap back and then again it will start from zero or something, and how to solve the problems with those situations so that there is no confusion with delayed duplicates. We have studied those things. Now TCP uses sliding window. The acknowledgement number contains the next expected byte in order. This is the next important concept. Okay, and it cumulatively acknowledges all bytes that have been successfully received by the receiver till now. This is a very, very important concept. Okay. For example, if the receiver sends any party sends a packet in which the acknowledgement number is 31245, that means the receiver has correctly received all the bytes up to 31244 byte number, and it is expecting byte number 31245 in the next segment that it will receive. This is an important concept. Okay, this cumulative acknowledgement is an important concept. Okay, so please understand that. Remember, in selective repeat, you can have gaps in your receiver window. Until those gaps are filled up, you cannot send back a cumulative acknowledgement for the entire range. You can only acknowledge up to the point till which all gaps have been filled up and you have received everything. So if there is a gap of even 1 byte, you cannot say that I will send a acknowledgement of something which is later on. I think there is a diagram somewhere. Let me see. Just keep over. So it is something like this. Okay. So say 2 kilobyte data is sent with starting sequence number 0. Then it is the stuff that is sent back from the receiver will have an acknowledgement number 2048 and window size advertisement of 2048 left, because it is supporting only 4096 byte sized window. Okay, buffer. Okay. Notice that the acknowledgement number is 2048 because it has received all bytes starting from sequence number 0 to sequence number 2047 successfully. And then it is saying that next I will expect something with 2048. Then again the application does a 2 kilobyte write, and that is maybe sent out as a single segment. Another 2 kilobyte segment. The sequence number starts now from 2048. It goes and fills up the entire receiver's buffer. Okay, because application on the receiver side has still not read anything. So the receiver's entire receive buffer is full. Now the stuff that receiver sends back, it can have its own data, but in its acknowledgement field, it will say that I am received till now successfully byte number till 4095. And the next expected byte number is 4096. And my remaining window size is 0. Okay, remaining window size is 0 because I don't have any space left. And anyways, the sender was blocked in the meanwhile because it was allowed to send total 4 kilobyte. It has already sent 4 kilobyte, and it has in addition got an explicit message from the receiver saying that the receiver window size is 0. So it blocks it. It cannot write. Finally, on the receiver side, somehow the application on the receiver reads 2 kilobytes, and that is removed from the buffer. When that is removed, the receiver sends another acknowledgement. This is another acknowledgement where basically just to tell it that the window now is partially free. But the window is not 4 kilobyte free, it is free by 2 kilobytes. So notice how repeated acknowledgements were sent from the receiver to tell the sender that, well, I have freed up some space, you can now send something. These are common situations where there might be no data sent from the one party to the other. So the receiver side is probably not sending any data to the sender side. But this second acknowledgement was essential to tell the sender that now you are free to send me more data. Otherwise, the sender was blocked. We have studied this type of an example earlier in the previous class also. Now, when the receiver gets a 2 kilobyte permission to send 2 kilobytes, it again may send up to 2 kilobyte, but it decides that, well, the next write is maybe 1 kilobyte because the application wrote 1 kilobyte and it said, okay, I had permission to send 2 kilobyte, let me send 1 kilobyte. So it sends a 1 kilobyte thing, okay, starting with sequence number 4096. And then when it reaches the receiver's buffer, it goes and sits in the it occupies 1 kilobyte space. Remaining 1 kilobyte space is empty. The 2 kilobyte that had been received earlier had still not been passed to the receiver. So I mean, it is processing data very slowly on the receiver side. So this is the situation. Yeah, just wait a moment. Now, although it seems that a lot of data can be transferred, okay, there is a problem. Remember that the network layer will kind of encapsulate the entire transport layer entity into itself to build up a large network datagram. There is a limit on the amount of payload that IP datagrams can support. Payload is the total amount of stuff encapsulated. Okay, because the IP itself has its own header, which it adds on top of that. The payload size maximum is 65515 bytes, which means obviously that your transport layer amount of data cannot be more than that. In fact, the total size of transport layer header plus data has to be less than that. Further on, when you go to the data link layer, typically you use Ethernet, which similarly has some limit on the amount of data it can. Remember that the data link layer will further encapsulate everything into another larger packet. And there, Ethernet and those data link, they have further severe limitation like 1500 bytes or something. Okay, maximum. So all these things, and this is called the maximum transmission unit or MTU, that parameter. All these things eventually mean that most TCP segments, it can be calculated, contains approximately 1430 bytes maximum. Okay, I mean, it seems that you could have sent a lot of data in one segment. You cannot. Okay, it's unfortunately this is the situation actually. So about 1430 bytes, 50 less than 1500 bytes is the typical amount of data that can be sent in a segment. Now, the MTU length might vary slightly along different paths. So nowadays, modern implementations first use something called a path MTU discovery. Okay. Using the ICMP protocol. ICMP is a different protocol used in the network layer. We will study later on. And it sets up a maximum segment size during connection establishment. Okay, it might depend on other parameters also, for example, how the buffers have been implemented, etc. But regarding the support of the path, the maximum segment size that the path can support, first it finds out. Why does it find out? Because there might be situations. See, it can be very defensive and say that I will make very small segments. Every segment will have only 100 bytes, and in that case, it is guaranteed I will never get into trouble because every link in the world supports segments which are as small as 100 bytes. Okay. Yes, that will work, but that is probably suboptimal. You could have kind of raised it till say 1400 or 1420 or 30 bytes. So why not let us find, or sometimes it might say, okay, let me always use 1430 bytes. But then there might be even more peculiar situations because given the network is very, very heterogeneous, that there might be some link which supports only up to 900 bytes. So in that case, your 1400 something length segments cannot be transported and there will be failures and then you need to come back to 900 bytes. That case, it is better you first find out what is the maximum length supported, say that as a parameter of the maximum segment length and you use that as a maximum segment length. You dynamically change the amount of data depending on the options fields that have been sent. Most of the time the options do not occupy any space. So other than the header, 20 bytes are gone. Remaining space you use for the data. Now, The window size is checked after receiving an acknowledgement. You set the window size on your side. Depending on the receiver window size, you set the sender window size. Then if you find that the window size is less than the MSS, you construct a single segment and try to send out everything at one go. Otherwise, you construct multiple segments where each is equal to the maximum segment size supported. Quite simple. Okay. Now, TCP design is very challenging because since segments are constructed dynamically, so retransmissions do not guarantee the retransmission of the same data segment. A retransmission may contain additional data or same data, usually. Okay. So if there is additional data, then that has to be taken care of by the the receiver. Okay. Otherwise, it will just kind of say that it will just reject say a received packet if it is exactly the same packet coming in. Okay, that it has already received. And the most important thing is that segments will arrive out of order. May arrive, they will arrive out of order. Okay, often. So then TCP receiver should be able to handle out of order segments in a proper way so that the received buffer space wastage is minimized. Okay, receiver buffer should be properly implemented so that out of order stuff will come in. There will be spaces in between. Okay, and gaps in between, but that gaps should be such that their management has to be proper. There should not be additional space wastage. Okay. Any selective repeat request will have the ability to receive segments out of order on the receiver side. So as we said that the window size is typically tells how many bytes the receiver can receive based on the current free size, that is buffer space. Window size B0 means there is no space in the buffer. Whatever it has received earlier is already filling up the buffer, and its application has not been able to remove it from the buffer as of now. But later on, when the application receives, the receiver on its own sends an acknowledgement packet segment saying that now some space is free. You may send some additional data. Okay. So the TCP acknowledgement is actually a combination of the acknowledgement number and the window size, and the acknowledgement number in turn is not. It is a cumulative acknowledgement acknowledging whatever has been received till now indirectly, but what it actually says is the next byte number that is expected from the receiver. Now, let's try to come to TCP connection establishment. It uses the three-way handshake that we have seen. It uses something called SYN mechanism. Okay. What is the SYN mechanism? Well, for this, suppose host 1 wants to initiate a TCP connection with host 2. It sends a SYN packet. What is a SYN packet? A SYN packet is something in which the SYN flag is set to 1 and the acknowledgement flag is set to 0. Okay. So remember that SYN and ACK are two flags in the TCP. This flag, 1-bit flags. Okay. So SYN, ACK, these are flags. There are other flags also, as we will see. FIN is the one used during the connection termination. We will come to it. So first is, don't confuse between the SYN flag and the SYN segment. Okay, SYN segment basically means it is a kind of a SYN flag. Now on the first segment, it might happen, it can have some data. Okay, so if that is it can say that I will use the starting sequence number X. Okay. Now, when the host 2 receives this, it sends back a sequence number. It proposes its own starting sequence number Y, and acknowledgement x plus 1. Why is this x plus 1? Because this is how it works. Okay, it is like basically, so effectively what would happen, the first data segment that would be sent probably will actually start from x plus 1. Okay. So although initially the first scene segment might have some data, might not have some data, it doesn't matter. But because when host 2 accepts the scene segment, it sends back an acknowledgement saying setting that, oh fine, I am okay with this. My next expected segment byte number is x plus 1. And when it sends back the scene acknowledgement, in that the scene flag is set to 1 and the acknowledgement flag is also set to 1. So there is a difference between the first scene segment and the second scene segment. In the first scene segment, the acknowledgement flag is 0 because till now host 2 has not sent it anything. But in the second scene segment, which is sent by host 2, it is saying that this is a scene segment, but it is also an acknowledgement. I'm acknowledging this. This has been sent in to acknowledge something. So the acknowledgement flag is also set to 1. Now, when this is received, host 1 says OK. So host 2 is proposing to use sequence number y. So fine. So I will set my acknowledgement field to y plus 1, saying that you start from this. And it sends its first data, which is sequence x plus 1. OK. So this is the first data segment that is sent by host 1. Sequence number x plus 1 and acknowledgement y plus 1. Initial sequence number choice we have studied in detail. The original implementation of TCP used a clock based approach. Clock ticked every 4 microseconds. Value of the clock cycle from 0 to 2 power 32 minus 1, and the value of the clock gave the initial sequence number. Okay, so this was kind of, it is slightly similar to what is used even now, but certain randomization components are further added. And then the mappings are more complicated. It is not always that there is a 4 microsecond clock tick. Okay, that is not always the case. Now, one problem with this connection establishment mechanism, there is a security implication in this. There is something called a scene flood attack, and I will finish with this in today's class. Notice that host 2, after receive the first scene packet segment, it commits to this connection without checking, or it has no way of knowing actually whether host 1 is actually interested to send it some data or not. Okay, because this third segment which host 1 sent, it doesn't know whether it will ever receive anything like this from host 1. So it commits saying that, well, yeah, I am okay with the connection. So it retains the state on its own side, but then it doesn't hear back anything from host 1. But that is occupying some resource on its side because it has opened the connection. It is maintaining some data structure by remembering the connection of the sequence number, acknowledgement numbers, etc., etc. Now it can be flooded by malicious attackers where several scene segments are sent in very fast, like in a short span of time. Millions of scene connections can be sent. It opens up these connections and then commits to these connections. It gets back nothing useful, and it hogs up all its resources. So this is called a scene flood attack. Now the solution to use is something called scene cookies. In scene cookies, the host 2 sends back its own sequence number by calculating certain cryptographic function of certain internal secret keys. It sends back the sequence number and then forgets. Okay, then it basically closes down in a sense that it forgets about the connection. It does not remember anything about the connection. Now, if it gets a segment back from the host with acknowledgement y plus 1, it says that, okay, somebody is trying to acknowledge y plus 1. Let me subtract 1 from this. When it subtracts 1 from this, it gets y, and then through the cryptographic reverse mapping, it verifies that, okay, yeah, I mean, this looks to be an authentic party who is responding to a previous connection request. Because nobody else could have been able to calculate y correctly. Only I can calculate y correctly. So I must have given the value y to him. That's why he's sending me an acknowledgement for y plus 1. Otherwise, he wouldn't have been able to send me this particular peculiar value. So this is an authentic connection, and then it continues the connection from this point. So it only commits after verifying that host 1 looks to be authentic. If some data segment that has been received from the other side looks to be authentic, only then it commits by dedicating and using up resources to handle this connection. Otherwise, after sending back the second thing, it kind of forgets about the connection. So this concept is called SYN cookie, and this kind of solves this problem of SYN flood attack, and it is implemented by modern TCP connections which are resistant to the simple SYN flood attack. SYN flood attack was a very common attack in the 90s when internet was becoming popular. Okay, but it no longer happens usually nowadays. Okay, so I will stop here. Next, we will study the connection release mechanism in the next class next week. Happy Saraswati Puja tomorrow, and tomorrow is a holiday. And best of luck for your class test on Saturday. Again, one earnest request is please do not send us handwritten stuff, and please do not be late in submitting. This time we will give you 15 more minutes to submit. So server will remain open till 5:15. Okay. No more emailing solutions, no more emailing handwritten and photograph solutions. Okay. Just write a text file or a doc file or whatever and convert it to PDF and submit. The entire file size will be 10 kilobyte or less. And if you take a photograph using your smartphone of a handwritten thing, that will be several megabytes. Okay, and of course, server will create problems. So many large submissions happening, it will freeze. Please don't do it and make life difficult for others. Thank you.